I'm working as part of a maths research group who are looking at a system of equations that are joined together in a way that we can model parts of the human brain on a computer simulation. The brain is obviously of interest because we all have one, and we're looking at ways that the brain might fall into problems, say with Parkinson's or epilepsy, and therefore ways that we might be able to help cure such diseases by stopping the brain from falling into these bad patterns where they do bad things. At the moment, we're actually focusing on insect brains because they're much simpler than human brains, but all the work that we're doing will scale up to parts of the human brain as well. To start with, we're looking at how insects smell, purely because, again, it's kind of the simplest task that we can look at, and then we can help classify what the insect is smelling, and maybe make a virtual nose, as it were, on a computer, so that you can stick it into a room and it'll say, well, it smells of gas, therefore it's dangerous, so don't go in there. Well, we have a system of equations that are fairly complicated, but they're all joined together in such a way that when they're running through a simulation, the equations will kind of link together. If you think of them as little balls going around in a circle, then to start with, they'll all go randomly around, but as you feed input in, they'll join together, and then with a system of 5 neurons that we're looking at now, they'll essentially snap together so that there's a range of 30 different states that these balls can go through. Obviously, when you've got 5 neurons and 30 states in the human brain, and you've got over 10 billion neurons, you're going to have a lot of states.